So we are currently recording. Audio, video look good. Okay. Let's switch over to Jupyter Notebook. So you should be seeing the Jupyter Notebook here, right? As you can see, it did the 4 epochs, and I already ran Learn Predict. So I really like that movie, okay? And as you can see, it said that this is a positive label. And it gives me basically from positive and negative, it gives me that it thinks with a probability of almost 0 that it's negative, with a probability of 99, almost 1, that it's positive. But I was also playing with another one. Let's do learn, predict, and let's just write something similar, but let's just say, I really did not like the matrix. I actually do like the matrix. I'm just an example. All right, so I'm gonna run this here, right? So you guys should be seeing. Right. So again, I guess in the video I should say we finished from the previous video. We were running the fastai.text text classifier learner pre-trained LSTM model on a fine-tuning it on a IMDb sentiment analysis problem. We can see here we ran 4 epochs in the fine tuning. The loss did go down in the validation, which is really where it's important. We see goes down, the accuracy goes at 93%. When I test learn.predict that I really like the movie, it classifies it perfectly. Now let's try this one. And you can see at first glance, I really did not like the matrix would be a negative comment. Do you see that the classifier made a mistake? Do you see that, guys? It says positive. Excuse me. But if you look, so that is an error. Think about the fact that this is a pre-trained model, fine-tuned, right? Maybe the fine-tuning, this tells me maybe the fine-tuning needed more epochs. Sorry. The fine-tuning needed more epochs, or maybe we just needed more data, right? Now, if you notice though, although it got it wrong, you can see here in the probabilities that actually this is a good sign, because here in the positive, it was extremely sure, right? So it's 99 to 0 basically. But here, negative was actually 0.42 and then positive was 0.58. So it was kind of on the fence. It went with pos, but maybe if I had done thing like, I really did not.
Could you replace take like out and just say I really hated the matrix?
That's a good one. Thank you. You read my mind. I was actually trying to think of that. So I really hated the matrix, right? That's what you said?
Yeah.
All right,
I'm assuming it was like on the fence because the word like was there.
Yes, yes, yes. I agree. So let's run it. What happened now? You see? I really hated the matrix is negative, and now it's more confident at 90% probability versus 10% probability. Do you guys see that? So one thing that I don't know if you've figured it out yet, but with just 3 little scripts using pre-trained models, you now have, quite frankly, one of the best sentiment classifiers out there, a good segmentation for autonomous vehicles classifier, and a pretty good classifier for cats and dogs, right? So if you think about it, the beauty of this is you literally now can do serious things. So, with this now you can do actual sentiment classification, really good. You can attack anything, Twitter. You have a pre-trained model, you fine tune it on your data, but you now have power, basically a lot of power. And that's the beauty of this. And a lot of it is state of the art, if you will. All right, now let's keep going then. Are there any questions about the text processing example? No questions? Everything made sense? All right, perfect. So now, so we've done image processing, we've done text processing. Another type of data that is quite common, obviously, is the CSV data, right? So we all get, CSV files. I mean, that's our initial inclination, is to just create CSV files of different things. So in this case, let's do a simple one just to kind of get some ideas going. This one, now tabular data don't usually have as much pre-trained models, right? So a lot of the pre-trained models have focused on text processing or image processing. These are the big things that like Google and Facebook, they're always after, right? Because they're Instagram, you post pictures. Facebook, I think you write stuff. And then so they're basically always trying to build models about this. Now, tabular data, that can be anything. If you guys remember last semester, we did ADSB data. It can be sensor data, all kinds of things, right? So in this example, it'll just be the standard CSV file. This will be related to determining if a person is a high income earner. So this will have something to do with some variables associated with the person, right? So it's the classic, kind of demographic example, and then you want to do a prediction. But it'll be a good introduction to the idea of a tabular example of CSV data. Now, again, remember with this one, this probably allocated a lot of memory in my GPU. If I run other models, they'll run out of, I'll get that error for memory error. So let's go ahead and address that again. So I'm going to go back. You should be seeing now my CMD prompt. I'm logged in to the GPU box. I'm going to do the command NVIDIA SMI. So if you can't see it there, let me go down a little. So I'm going to do NVIDIA SMI, and then you can see PyTorch is allocated right now some memory. I'm just going to get rid of it because, so if you notice, my NLP, my text processing LSTM, that was actually pretty slow, did not error out with memory issues, which was great to see, right? So I'm going to get rid of that one, 11284. All right, should be gone now. And then if you double check NVIDIA SMI again, you can see it's gone. So the cache, whatever of the GPU is clear, the GPU memory usage. And so we can go ahead and allocate a big job to it again. Let's go back to the Jupyter. Now, I've already posted these Jupyter notebooks on my GitHub, so I don't need to save them. Let's go ahead. We've done movie reviews and segmentation. No, sentiment classification and segmentation, I believe. Let's do now the tabular data of adults and their demographics. So let's do that. I'm going to close this. Okay. I'm going to create a new one. So I'm going to switch to the Jupyter Notebook. All right. And again, the same pipeline as before. So this is, from fastai. AI dot tabular dot all import all. Okay. And then I'm going to do the path again. This is our data. Now, one thing about this is here, we are not pre-training. And that's what's really, or we're not using a pre-trained model. We're actually going to train this model from scratch, okay? And that's actually one important thing because it shows that this pipeline actually works for us to also just have our own data and train all the weights from scratch. And so you'll just see the slight differences in this approach. But as I said, we're not really still, we are not yet getting into all the details. We're kind of just doing a high overview of things, okay? So let's do untar over here. Untar data. And then we're gonna do URLs dot adult sample. All right, so adult sample, it's just a data set that we're going to use. Remember, our goal is, high income earner type of a thing. Okay, so now CSV, I should say, is comma separated files. Okay, so I've got adult sample there. Now the DLS, remember, that's just a data set with all the transforms. So in this case, I'm going to call yet another one called tabular data loader. These data loaders are more and more popular with everything nowadays. So certainly makes sense. And then we're going to say from CSV. Here we have to specify a lot of parameters. For this one, because it's CSV data. So we're going to have to specify the file name. So we're going to go over here, path. So I said from CSV, right? So path, it's going to be adult CSV is the name of the file. Okay. Path equal path for that adult sample. Y names, so the label is in salary. Remember, we're talking about a CSV, so we've got some columns in there. So Y names salary, comma. And then we need to specify the fields, right? So we have a comma separated file, we have the labels, and then we have all the different features. Some of them are going to be categorical features. So that's the kind of thing where it's like education, might be like, undergrad, grad. But you also have quantitative values like age. So age is going to be numbers, quantifiable numbers, the age. Whereas other ones will just be occupation, etc., that are demographic. Okay, so we have to specify those. So I'm going to say here, is it salary, categorical names, and you just really have to specify from your file these as a list. So single quote is going to be work class, comma, education, comma, marital status, comma, occupation, comma, relationship, comma, race. Okay, and then over here we have the continuous fields. So continuous names, because you have to tell it which ones are what. So in this case, again, create a list. And these are going to be age, comma, FNL WGT, I think is weight probably. FNL WGT. And education number. So education. This is just specific to that file. Num. All right, so I specified the fields in there. Now you also specify a few like transforms that you're gonna do, like the ones we've always done before. So things like normalization, etc. So here, categorify. Okay, we have fill missing data. So you can see how it's got a lot of handy things. So fill missing and also normalize the data, which, as you know, you should always do. All right, so now that you have this, remember, we had to do all these transforms. Remember, we are training this from scratch. We don't have a pre-trained model for this one. So then we're going to do learn.tabular learner. And that's should not be a dot. So tabular learner this time, right? That's the model that we're using for type of CSV data, as I said. And then DLS goes in here. And also the metrics that we're going to use are accuracy. Accuracy. So we've got our metric there, accuracy. Now notice here, I'm going to do learn. Now we usually do learn fine tune. Here I'm going to do learn fit one cycle. And then you can actually specify how many cycles by putting in a value. So for instance, 3. So it's 3 epochs basically of looking at the data, the same data set 3 times. But I'll add a comment here. No transfer learning here. Just train from scratch, basically. Okay, so that's the idea. And now if everything is correct, we should be able to see the model perform and see the accuracy of it. So let's go ahead. Go ahead and run it. Here. I think I'm missing a comma probably. Yeah. Comma here. Comma. All right, let me clear the kernel. All right, I'm going to try this again. There we go. All right, so it's training from scratch, and look, it's pretty quick. And it did the 3 epochs basically. It gets basically a validation loss, goes down. The accuracy is around 83%. If we do more than that, say 20, run it. Let's just see what happens. Any questions, guys? So far?
Nope.
Making sense? All right. Good. All right, so let's see. And it actually did not improve that much, huh? 83, 84, 84. Stays pretty constant at 84. All right, yeah. So that's the best we can achieve with it, but it's something. So as you can see, that's an example of doing with a CSV, which, you know, here in FastAI is called tabular. And basically, we also trained from scratch. We didn't actually import a model for this one. Okay, the model is about 80% accurate, right? Yeah, 84. And it was really quick to train. All right, so it seems like there were no questions on this one. So let's do, I think I have one more, I believe. All right, so let's go ahead then and take a look. All right, so the next example that we're going to look at is a recommendation system. This one's a little bit different, but it's also going to be based on, I guess this is called collaborative data. So let's take a look. All right, so this is going to be the, it's a recommendation system. As you know, a recommendation system, I guess I should define a recommendation system is basically a system that, like with Amazon and Netflix, right? So they're always recommending products from the Amazon store, you know, so that you buy more, or movies that might be within the categories that you like. So basically the idea is to recommend things. So data sets usually have a rating, you know, for this movie, the rating is from 1 to 5, or for the product is from 1 to 5, 5 stars, 4 stars, etc. So that's where the data, that's the type of data that we're using. Okay. All right, so we're going to be using for this the movie lens data set. Okay, movie lens data set. All right, so let's try this one. I'm going to go back again to video. So you should be seeing the command prompt. I'm going to run NVIDIA SMI. As you can see, there's allocated in memory. I'm going to get rid of that, given that I just don't want, you know, I want to have as much memory possible. So 758. So kill minus 9, 157. All right. I do clear, and then I run NVIDIA SMI. You can see that it's gone now. So let's go back to the Jupyter. All right, I'm going to close that window. All right, so I'm going to create a new one, new Python 3. All right, there we go. So, and I'm going to make sure I'm sharing this screen. So this is going to be a recommendation system. Okay, recommendation system. From the movie lens database. So we're going to call from fastai.colab. Fastai.colab import all. We're going to call path. This will also be this model will not be pre-trained. So we're just going to have data from scratch. By default, when there's no model, just FastAI just does pre-training, or does training from scratch. And that's kind of how it works. So in this case, we're going to do path on tar data. On tar data URLs dot ML sample. DLS is actually the data set as we've done before. And now we use the Colab data loaders for these collaborative things. Forget the term for this. I think it's like collaborative filtering or something. So ML sample is just the movie lens. And then Colab data loaders, we're going to load this from CSV. So it's kind of a tabular one as well. So dot from underscore CSV. This is going to be path. Oops. Ratings dot CSV. So that's the file, ratings.csv. And that's pretty much all that we would need. And now we can just call up the learner, learn. And this is a Colab learner. Colab learner. It takes DLS. And it will also, and now we need to specify, because this predicts ratings, it doesn't predict classes. So this is going to predict a Y range output of that we can specify. So we just say from 0.5 to about 5.5, I think it is. Yeah, and that's the rating scale that we're going to be using here. And now, notice here we're going to do learn. We could do fit one cycle, but actually we can also do fine tune, just like we were doing before. And because there's no model, fine tune will just basically train from scratch. Okay, so that's basically all that we need to do. So now let's go ahead and run it. So this is, we probably should call the other library because it's not finding on tar. So let me do.
I call it tabular.
Yeah, exactly. So I'm doing fastai dot exactly good catch. So tabular dot all, that should have the function import. Okay. Let's clear this one, the kernel. Okay. So I'll make a note here that we can still call fine tune even though we are using we are training from, okay. So that's basically the example, and then we can also do learn show results. So this way we can see some predicted movies and their rating. So based on the database, of course. So learn show underscore this. Okay, so show results. So let's go ahead and run it.
You forgot your S in CSV.
I forgot what time.
The S in CSV, ratings.csv.
Thank you. Yep. With a kernel. All right, now I'm gonna run it. And there it goes. It's going pretty fast. It trained, and then after that, it gives us actually, we have a user ID, we have a movie ID, right? The movie, and then the rating that is given to it, and the rating predicted. So you can see they seem to be consistent. This is a type of a regression, not a classification problem. It's just predicting a value there. So it's predicting movie ratings on a scale, as you can see, from 0.5 to 5. Because it's predicting quantities there, we have to give it this range. Now remember here, we are not using a pre-trained model, and instead we are training from scratch. And notice that we can use fine tune. And then later on in the semester, we'll take a look at, more of those details. Okay. And that's it. So that's a nice example of some of these. Are there any questions, guys? So today, that's what one of the things that I wanted to show you is basically to do a few more of these. And now you have a kind of a sense of the power that you have, right? So now, think about it. You have this thing for movie reviews now, right? You have, so you have all these models. You've seen how to train them from scratch. You also have built-in very powerful models, etc. Okay. Any questions? No questions? All making sense? Yeah, all right. So it sounds like there's no questions. So I'm gonna once again go to the terminal, clear VSMI. You can see there's something in the memory there, GPU memory usage. I'm gonna get rid of that one, 15967. All right, I'm gonna do clear here. Okay, so the next thing that we're gonna look at is something very, very interesting, very powerful. So let me just come back to Jupyter. Close that. All right, so let's go back to Brightspace. So I don't really have a homework assignment to give you guys this week. Okay, just practice the FastAI examples. We are going to take a look at something else now. More FastAI. I'm just going to add the link to the code there. So the code that we did today is here in basics. You can see that there. So just going to provide. Here, I'm just going to create a link code so that you can take a look at the code. All right. So the next thing, the next module we're going to cover today is we're not going to get into the transformer algorithm just yet. So I'm not going to call it transformers. Instead, I'm going to call it Huggingface. And that's an actual thing. I don't know if you guys have heard of it, but Huggingface transformers module. Just want to make sure I get that spelled correctly. .co. Yeah. So Huggingface is transformers module. Okay. So what is that? So first of all, what is Huggingface? Have any of you heard of something called Huggingface? What is it? Anyone know? Can you guys hear me?
I got no
Hmm?
idea.
No idea. Okay. Yeah. So Huggingface is it's a company. It's a group of people that work in AI, and they've created a small company called Huggingface. I think there are about 80 people right now. It's a startup. It's similar to FastAI in a sense. There's some similarities. They've also just like the FastAI people developed the FastAI library. They have developed a library for transformers or transformer modules. So they basically are a little bit more specific towards natural language processing. So let's actually go to their .co. So you can see that there. So that's that little emoji or whatever from the phone. That's where they get their name from. But they've developed a pretty interesting thing. And I wanted to point out to you how probably this field of data science and AI is going to look in the future. So what they do here, this is a hub online where people basically exchange models. So you can see that there, right? So you have all these models. So for instance, you have this from Cardiff NLP, right? So it's a research university. Helsinki University. And then you have like, pretty sure there's like Google, electrosmall discriminator, and I'm pretty sure there's like a Facebook in here somewhere. There's Helsinki again. There's Facebook. So what is this? It's pretty interesting, actually. So if you think about it, what you guys do, you want to build, let's say, an NLP model or any other model. So you have some great, so your Google, Facebook, obviously you have tons of data. And then you train your model. And then other people, just like we've been doing with fastai, many people will want to use those pre-trained models on their problems, right? So what they can do now is they've created this hub where people load their models. And let's say, for instance, I'm just going to pick on one of you. Let's say Kyle, right? Kyle is doing some intrusion detection system, and Kyle has some unique data and has a lot of that data. So then Kyle builds a deep neural net and trains it on that deep neural net. And now Kyle is going to share the model. So he's going to share the weights, you know, that kind of thing. So they've created this hub where you can actually load up the models, and now they're available for you to use. So then you'll do the same thing, transfer learning, you'll download the model, fine tune it. Probably, let's say you did intrusion, or you did intrusion detection, but really that's networking in general, right? So let's say that Kyle's model, he shares the networking aspect because he actually did a multitask where he did intrusion detection and other things. And then the model's available. It's really good at detecting network data. Excuse me. And then you want to apply it to network management, for instance. That's your problem. Classify something about network management. So you share it up here, and then people can use it for their ideas, okay, for their own projects. So that's really the idea. And so this is a very interesting community. What they developed really is a library called the Transformers module. It's a Python library built on top of PyTorch and TensorFlow, deep learning. And so you can download all these pre-trained models, and then you can basically share them and use them and so on through this library, okay? So one of the things that we will cover this semester also is this. Now, this is usually built on top of transformers. You can see that that's pretty obvious there. There are two types of transformers, just the encoder type architectures and then the encoder and decoder architectures. We'll analyze those, but basically just be aware that they like to name these transformers. So for instance, one of the first ones is called, I think, the I forget the name, but like the bidirectional encoder something architecture, and they give it names like Bert or Albert or Roberta, right? Because they're derived from the original Bert. Or they have other names like, if we go, I think I saw this in the first page. There's Distilbert. Distilbert is like a distilled version of BERT, so it's actually smaller, something like that. GPT-2. GPT-2 is from OpenAI, and it's an encoder-decoder architecture. This one is supposed to be very powerful. I think it just means generative pre-trained transformer, I think it means. So that's GPT. They're up to GPT-3 now, which just came out. They just made apparently the code available recently. So anyway, it's, you know, this is very consistent. It's still transfer learning. It's the same idea. You download BERT, and then you download the model of it, and then you adapt it to your own problems or use it, or you can actually just use it out of the box, right? You can just use it out of the box. So we will be exploring that this semester, okay? But one of the big ones in this is this company, Huggingface. as I said, because really what's, I like two things that they've done. One thing is this hub for exchanging your models. I think that will definitely be a big thing in the future that everyone will do, so that all of you, for instance, who are doing, let's say, a thesis or a project, it's no longer just sharing your data and the papers. Now your model will actually also be of interest. So they've done that, the hub, which I find very interesting. The other thing that they've done is, which is, that's a lot of work, but they developed the Python library, which works, it works really nicely with PyTorch. It's a little bit more finicky with TensorFlow, just because TensorFlow is constantly like in flux, I think. All right, so that's basically the idea. Okay, so hopefully that makes sense. As I said, I'm not getting into the model architecture just yet. Instead, I want to just discuss some of the things that we can do with it. So I'm going to go ahead for this, and I'm going to need to switch back to all right, yeah, so let me share. You should be seeing my terminal. I'm going to go into my GPU box, and we're gonna exit out of FastAI for now. Now, the plan that I have is I'm gonna go through FastAI in more detail next week. So today I'm just kind of talking about transformers a little bit, but my goal is to get through FastAI, and then towards the second half of the semester, we're gonna get into transformers. Okay, that's kind of the plan. But today, just really quickly, so let's look at some examples. So I'm going to navigate into my folder for transformers. You can see I have several examples here of some classifiers. I have several for fine tuning. These are like the more advanced ones. But basically you can see here, I'm fine tuning a BERT model for multi-class classification, or I'm fine tuning a BERT model for single sentence classification, or I'm fine tuning a distill-BERT sentence classification, but in native PyTorch, which basically means you can either do it in pure PyTorch or use a lot of PyTorch, or you can use the transformers module, which has a lot of functionality as well. And so you can do that. You fine tune in native PyTorch over here, fine tune pre-trained model, and so on. So these are the more advanced ones. There's a few other things that we can do, like manipulating data sets, metrics, right? Model trained from your data, just simple training. And then I have a few examples, which is really what I had planned to do today, is I have a few examples of just out of the box models that have names, right? So as I said, these are, without getting into too much detail, remember, it's just a neural network, deep learning set of architectures where it takes as an input something. And usually it's, because we're doing NLP here, it's going to be a sentence, right? A sentence, a sequence of words. We take that in as input, and then we do something with it, okay? Like predict a class, or maybe if we were doing sequence to sequence, we might have, let's say, like an English sentence and translate it into a Spanish sentence, for instance. Notice here, I was playing with this Turkish text classification module just to see how that works for other languages. So we've got, and then when you deal with NLP, one of the big things that you deal with is tokenization. So tokenizing just basically means, how are you going to represent your text? So usually every word becomes basically like an ID, and then this ID points to a vector. So, you're going to take every word and try to represent it as a vector in a vector space that is specifically learned. Okay.
Is it a character vector? Or,
Sorry, say that again.
what kind of vector is it?
It's going to be a vector of, so basically you take a sentence, right? And then you're going to break it up into words. Then sometimes you can break the words up into subwords. So for instance, happiness, right? You could, or happy, or what's something that I don't know? Sleeping, right? Sleeping is a better example. Sleeping could come from sleep, and then there's the ing at the end, right? So there's processing now that can take sleeping, break it up into sleep and ing, and that actually allows the models to learn a little bit better. Because whenever it sees a word that ends with ing, it kind of understands that there's a specific meaning associated with that. Do you see that?
Okay. So can it start to interpret like tenses then, past tense, present tense?
Exactly. It's better at that. And then if I switch to the whiteboard to answer your other question about how is it represented as a vector. So usually in the past, you've probably learned that you represent a sentence as a bag of words approach, right? You guys remember that? I think we probably did something like that. So that is to say, if we have a vocabulary of 10,000 words, 1, 2, 3, all the way to 10,000, then word 1, let's say happy, would be represented as something like that, right? But nowadays, you don't do that. Instead, a more efficient way of representing words is by word embeddings. And what that means is that you're gonna use an algorithm, which is usually called word2vec or something else. It's gonna create a list of words. So let's say happy, hello, car, boat, cat, and so on, right? And every word is going to be represented, as a word embedding. Okay, it's gonna be associated with an ID, 1, 2, 3, 4, 5. But now, whenever you give something to the model, you're actually gonna give it the word embedding. They all have the same dimension, and it's actually not very big. So you'll usually do from like 1 to, let's say, 128 or 256 features at most. You see that? So every word is going to be represented like this. And if you have a sentence, let's say the cat is sleeping, this has 4 words, right? So really, it will be a matrix of basically 4 vectors in this order. So each one, and this is from 1 to 128. Oops. So this is what you provide to the network, to the neural net. Now, the question that you might ask is, how do you learn these values, right? The 128 values, because those have to be learned. And usually with transformers nowadays, sometimes you can actually learn them separately, but nowadays it seems that you can actually just leave them blank and you let the transformer figure out what those values should be. It's a similar idea in a sense to when we talk about CNNs, and the CNN is going to figure out the filters, right? So here we have a similar idea where the transformer is going to figure out what the dimension should be. You only really define the dimension, but you don't define what these values should be, and instead it's going to start learning them on its own. Does this make sense?
Kind of, I have a better idea of what you mean now.
Yeah. So this is the input, right? So the input is you have sentences, right? The cat is sleeping. This is going to be fed into a model. Usually you have an architecture called the encoder decoder. And so you're going to feed it an input, you're going to get an output. The encoder, the basic idea is that you take this sentence, the encoder will do literally that. It will try to encode it into another vector. There's a lot of encodings going on, like, you know, like that, very sequential. And then sometimes you might have, like, let's say that you're doing translations. You have English and Spanish sentences, right? So what you do is you feed the Spanish here because you're trying to predict Spanish over here. And then you feed the English in the encoder, which gets encoded, and then that feeds into there. So that you transform one of the inputs, encode it, and then you have another input that also goes into the model. And then at the end, you get the translation because you're teaching the model how to translate, let's say, from one language to another. But this is just one of many tasks that you can do. This is just a good one for showing that you have this architecture of encoding, which is basically taking an input like this one, producing an output like that, and then it passes, and then the decoding is kind of trying to arrive back at the sentence given other information. Now, one thing that's really important, as I said, is this, the representation of these words as this, the vectors of 128. Now, there's something called GLOVE, for instance, and what I forget the acronym, what it stands for, but it's basically like pre-trained vectors. So they took a really, really large data set, right? And they just they learned all the vectors. So then now, whenever you have a language problem, you don't even have to do the vector training because chances are you're not going to have a data set as big as they did. And so instead of giving it your data and then getting a 128 vector for cat, all you have to do is instead look up the vector in GLOVE and then use that. The representation of cat as a 128 vector. It learns it on its own. So now, how does it learn things? It learns things by correlation. So usually when I say, the cat is sleeping, or I say the cat likes to meow, right? Meow. So you usually associate these two words, right? Cat and meow with the same thing. You wouldn't say the cat likes to dance, right? That wouldn't jive there that well. And so in a vector space, what's going to happen when you have cat, because it's a vector space of words, you're going to see that cat and meow are closer than cat and dance. Do you see this, guys?
Yep.
Yeah. So imagine now the following scenario. Without understanding the algorithm, just think about the following scenario. You have a vector space, right? It's obviously much bigger. It's in fact of size 128. Every word that you want of the most frequent words, let's say that the 70,000 most frequent words, you're just going to throw in here, right? You throw them in there kind of at random. So they're all at random, like kind of there. But then your algorithm, it's going to read the text, right? And it's going to say, for instance, as I said, meow is over here, cat is over here. But whenever the model reads cat and meow, what's going to happen? It starts to realize, hey, you know what? These two are close. Do you see that, guys? And so the dimensions of this space will start to get adjusted and will start to develop meaning to the point where when the algorithm is finished, if you will, when the algorithm is finished, cat and meow should be close to each other, whereas dance should be far away from cat because it doesn't occur. They don't really occur together. If you have Washington, D.C. and the USA, right? Whereas Paris will not be as, Paris will not be as close, but it could be close because they're related. Now notice another thing that could happen is, notice this relationship of Washington to USA, so Paris to France could also be captured by the vector space. Okay, so this is called vector representations. It's one of the topics that we'll cover this semester. This is how text is represented nowadays in deep learning. Any other questions, guys? So with that being said, then, you know, we train these extremely powerful models. BERT was trained by, I think, Google or Facebook or one of them with all the data that they have, which is a lot. GLOVE was trained with a lot of data also. So you have the vectors now pre-trained, you have the models pre-trained. And so, and then people just start making modifications. So you notice, for instance, here, I have Albert test, BART test. BART is actually an autoregressive model. We've got Electra test, that's another one. Roberta, and so on. So these are just transformer models that have been trained on a specific data set with some specific architecture and for a specific task, and then people have made them available for you to play with, and it's and you can fine-tune them as well, as we were doing with fastai. So for instance, this is an example of Albert using the transformers module from Huggingface. So you can see here I have some, that's it. So you can see the code is actually quite short, and thanks to the transformer module, I can actually do some interesting things with it. Okay, let's take a look at another one. BART. You can see BART here is an example of a summarization module. All right, so basically here from transformers, so notice the syntax, although we're not getting into the code today so much, but I just wanted to do a short demo. So from transformers, import auto model, pipeline, BART tokenizer, BART for conditional generation, BART config, right? So these are, again, things related to transfer learning, you know, a tokenizer that's already trained, an auto model that allows you to load the model. You specify that you want a pipeline for summarization. So that means you're going to take some text and make it shorter. So a summarizer. Then what do you need? You need a model. So you call BART for conditional generation. Notice dot from pre-train. So when you say this, notice now we're making a reference to the hub at Huggingface. So this says Schleifer Distilbert CNN 12.6. So basically, it's a CNN Distilbart module from this organization. We also need a tokenizer because we need to have a way of converting the words into like encoded values, okay? And this is usually that's just numbers, right? So like not even the vectors, but just, you know, like an ID, like 17 is the word cat. So that because the model was trained on that tokenizer. So then your data also needs to be within that tokenizer. But notice here, basically you define the pipeline, which is what you want to do. You define the model that you're going to use, something from Huggingface, this one. You define the tokenizer here, BART tokenizer from pre-train, and then the same thing, the still BART. That's the tokenizer. And then after that, you form together the pipeline here, summarization, the model, the tokenizer. Then I just took an example of some text I found on Wikipedia. And then I applied the function NLP, which basically should do summarization. So it should summarize. So I printed the original, and then the new one, it was okay. I mean, I didn't think it was that great, but let's go ahead and try it out. So for this, I'm gonna need to be in another, so in another environment. So I'm gonna do conda activate Pi transformer. That's my library. Supports PyTorch only for this. And is it Bart? Yeah, Bart. So then Python Bart. You can see it's trying to contact Huggingface there, trying to get the models from their hub. And then it's already pre-trained, so it shouldn't be. And then there you have it. This is an actual summarization transformer. So here's the original text. This is the output of the transformer. So if you guys look at this, what do you think it did basically? You analyze the output compared to the input. What do you think it did?
Seems like it grabbed what it considered the most like important of all of the sentences.
Is that what you think it did?
That's what it looks like to me.
Yeah, so aviation is the activity surrounding mechanical flight and the aircraft industry. Aircraft includes fixed wing, rotary wing, morphable wings, wingless lifting bodies, as well as lighter than aircraft, such as hot air balloons and airships. Aviation began in the 18th century with the development of the hot air balloon, an apparatus capable of atmospheric displacement through buoyancy. Some of the most insignificant advancements in aviation technology came with the controlled gliding flying of Otto Lilienthal in 1896. Then a large step in significance came with the construction of the first powered airplane by the Wright brothers in the early 1900s. Since that time, aviation has been technologically revolutionized by the introduction of the jet, which permitted a major form of transport through the world. The summary is just aircraft includes fixed wing, rotary wing types, morphable wings, wingless lifting bodies, lighter than air, airships. Aviation began in the 18th century with the development of the hot air balloon, an apparatus capable of atmospheric displacement through buoyancy. What do you guys think?
You just grab the second and third sentences.
That's what it seems to you?
Yeah.
So one thing that, again, I do think about transformers is that if you look at the summary text, it may not have grabbed it. It may have done something a little bit more than just grabbing it. But if you look, the output is not wrong in the sense that there are no errors in it. Do you see that? It's like grammatically correct. It's missing that certain thing that makes humans smarter than computers. You know what I mean by that, guys? It's just missing that little insight that we humans have to be able to read this and provide a good summarization. We can do that. The transformers can't do that just yet. But if you look, the output is grammatically correct. And I know you're going to say that it just took 2 sentences out of the 5, but you'll see later on with transformers that that's not all they're doing. They're actually generating text from scratch, word by word, and it's not always just like picking a couple of sentences. But I like this example because it kind of drives that. I didn't particularly think that it was a good summarization. Certainly we could play with this more and do a test like, is it always just grabbing a couple of sentences, something like that. Does this make sense, guys? Questions? So as I said today, you know, I just wanted to show these pre-trained ones, just to kind of show you because this is also fine tuning, but with an extremely powerful library from Huggingface. Let's take a look at Electra. So look, Electra, I don't know if I got this one. Yeah, I like this one actually. So look at Electra, that's all it is. Now, obviously, these are just very basic. So that's why they're so short. Actually, when you start to do something meaningful like fine tuning, they're much larger than this. But look at this one. So from transformers, import Electra tokenizer. And then Electra then tokenizer, we, again, from pre-trained, so we have a Electra small generator from Google. So they, you know, Google developed this model with all their data, and now you can use it. So then you have a tokenizer of a lot of words, right? Because again, you have to be, like if Google determined that the word boat is 17, then in your data, boat needs to be 17, okay? That's why you need a tokenizer. And then notice over here, you do from transformers, import pipeline, import pandas as PD. And then now look at how interesting this is. So this is Electra. I believe Electra is a BERT type of an encoder, I believe, if I remember correctly. So what they do with these transformers is that they would give it 2 sentences. You know, the cat is sleeping. But then in another sentence, they would say the cat missing word sleeping. Or the cat is missing word, and in another sentence, the cat is meowing. So the model is supposed to learn to fill in the blank. And they've used this approach to kind of teach the models. And so you can see here, this is kind of what is happening here. You have a pipeline fill mask. The model is from Google Electra small generator with the tokenizer that we already trained, and then fill mask then gets applied. So fill mask, the cat is very, and then mask. And the model is going to try to fill in that word. Do you guys see what's happening here?
Yeah.
Okay. And then the mask token, we can print it out. So let's go ahead and run this one. This was Electra. And as I said, these are just like, we can get a feel for them. But let's run it. And there you go. So it provided some, the mask is that, and so we can see here, provides the scores and the token that it predicted. So in this case, the token string. So the cat is very friendly. The cat is very cute. The cat is very sensitive. The cat is very shy. The cat is very smart. You see, and you can apply that. You can use literally this for anything, right? I just picked an example, but because these are very large pre-trained models on millions, I think we will at some point look at what GPT-3 did. They used a massive, and I mean massive amount of data to train it. So it really learns a lot of things, right? You could say, I don't know, you could say the goat on the mountain is, and then it's gonna, oh, actually, let's try that one. So let's do, So that's the beauty of these, is that these are literally like NLP agents that have learned something about the world, and now you can try them out on your own problems. And there are many things that we can do. This is just like the tip of the iceberg, if you will. So let's just say a goat on the mountain will, and let's just say math. Let's see what it does. See that? So then it should fill that in, hopefully, right? So the goat on the mountain will, what would you guys say it should say? Like before we run it, like you guys are, you know, what would you say?
I don't know what they call it, but do the goats bray, or like, what do they call the noise they make?
I have no idea, but you think that's what it'll say? The goat on the mountain will
Possibly, or jump, or
jump. Okay, jump is a good one, right? So let's try it and see what it does. I don't know. It just occurred to me to run this, and this is definitely a pre-trained model by Google, so there's something there. Okay, so we run it. It's thinking. Why is it taking so long?
have you ever seen the goats climbing way up mountains just to lick salt?
I've seen him climb mountains, but not the what you say about salt.
Yeah, like the sheer cliff faces, like vertical. They climb. It's crazy.
Yeah, I've seen. That's amazing. What happened? Why didn't this? Because the other one ran, right?
Because there's no period by any chance, or
You know,
does that make a difference?
well, no, I think maybe that I have two data frames, maybe. I hope that's what it was. I'm gonna just comment out one. Because the other one ran pretty fast. Let's try it. The model's already trained. It's literally just applying itself. I don't know, this was working a second ago. Let me check the SMI memory. It's taking longer than the first one, right, guys? We'll end with this today. Let me just, yeah, there's nothing in memory. That's disappointing. Let me just put it back to the way it was.
Should you maybe get rid of like on the mountain, just the goat will?
Say that again, sorry?
Should you get rid of on the mountain and just do like the goat will? Like you did the cat is very.
Oh, you mean just make the sent? Let me just see if this one runs again, because oh, there. See, this one ran pretty fast, right? So what's the issue with the other one? What I mean, I see your point. What did you suggest I should change?
Get rid of on the mountain and just do the goat will.
Okay. Yeah, maybe. Although in theory, this should have worked. I don't know why. Huh.
They call the noise they make bleat. By the way, I looked it up.
All right. There. Oh, see, yeah, yeah, you're right, Kyle. You somehow. So the goat will die. The goat will eat. The goat will feed. That kind of makes sense. The goat will sing. Probably not. The goat will suffer. Yeah. Now, why didn't the other one work? The goat on the mountain. Maybe I just couldn't resolve it, I think. I don't think this is a very long sentence. And these models handle like 40 token sentences, I think. Did it work this time?
Hey, it worked.
So we
Yeah, so let's see. So the goat on the mountain will die. Well, I guess because on a mountain you can die. Think about it. Although initially it had said that it would die. The goat on the mountain will feed, eat, will be. The goat on the mountain will survive. So,
I like the last one.
so it can't really make up its mind. But yeah, you see the how this is interesting, guys. So certainly transformers are an amazing thing, and we'll spend, like I said, my goal is to spend the second half of the semester on this. So we're going to take a look at all of them quite a bit. I just wanted today to kind of lay out some of these. I'll be posting these on Brightspace later. Sorry, on GitHub. I only did Albert, Bart, and Electra. There's also Roberta. Roberta, I've heard, is a little bit more advanced than Bert. Yeah. And then GPTs, I don't have any of the GPTs in here. But anyway, that should be it for today. Okay. So just in summary, today we continued our look at pre-trained models. As you can see now, you have a lot of classifiers that are extremely powerful, and you can fine-tune them for your own problems. We looked at FastAI examples of tabular image processing and text processing. We saw that RNNs were extremely slow, LSTM, but then I've introduced the transformer modules from Huggingface, transformers, and I've introduced just a few little examples of the various models pre-trained by Google, Facebook, and so on. All right. These are models that, as we did today, we can just use them off the shelf, if you will, or we will learn later on, like the ones where I usually put fine tune in front of it. It means that we're taking that model, but with some data, we're going to fine tune it for our purposes. All right, so this concludes today's discussion. We will meet again on Monday, and on that day, we will go back to FastAI just to get more into the details of it. And then maybe I'll show a little bit more of transformers towards the end. But this topic, I'm like I said, I'm probably going to cover it at the second half of the semester. All right, that's it. I don't have a homework assignment for you guys for today. So just work through all these examples, get your GPUs going. And then hopefully I'll have a homework assignment for you next week, which will be week 4, if I'm not mistaken. All right, so I'll stop the recording at this time.